So today we will start module 6. Okay. Quantum physics. Quantum physics. So why we go for the quantum physics? Till now we know the classical physics or the Newtonian physics. Okay. Now why we go for the quantum physics? Because Newtonian physics or Newtonian mechanics or the classical mechanics is applicable for the macroscopic particle. Okay, macroscopic particle and whose velocity is very low. Okay, like the cricket ball, football, train, bus, plane, etc. These are the macroscopic particle or macroscopic body. But when we go for the microscopic particle or the subatomic particle, and if the speed or the velocity of the particle is comparable to the speed of light, if the speed of the particle is comparable to the speed of light, then it is not possible to explain the behavior of the particle with the classical mechanics, and those particles cannot obey the Newtonian mechanics. Okay, so that is the first thing to go for the quantum physics. That means when we go for the subatomic particle. Okay, subatomic particle like electron, photon, neutron, etc. Okay, and whose speed is comparable to the speed of light. And you must remember that the speed, if the speed of the light is comparable to the speed of the if the speed of the particle is comparable to the speed of light, then that is called relativistic particle. Relativistic particle. Relativistic particle. If the speed of the particle is comparable to the speed of light, if the speed of the particle is comparable to the speed of the light, then that particle is called relativistic particle. Okay, so in quantum mechanics all the particles are relativistic particle. Okay, in quantum mechanics all the particles are relativistic particle. Relativistic particle. Now there are some phenomena also which cannot be explained by the classical mechanics. What are those? What is the phenomenon or what is the effect which cannot be explained by the classical mechanics?
So, wave nature or particle nature.
That is the photoelectric effect. Okay, we cannot explain the photoelectric effect with the help of the classical mechanics. Who invented photoelectric effect? Not Einstein. Hertz. Okay. Hertz. Hertz first. Not explain, found the photoelectric effect. How he found it? He will experiment. He was doing some experiment with an electrolyte. Okay, and in the electrolyte there is two electrons, and he saw that when some light is incident on the electrolyte, the current is passing through the external circuit. Okay, but he cannot explain, and he repeated the experiment and he got the same result. But he cannot explain this. Why? Because at that time he don't know the quantum mechanics. There is no quantum mechanics. He wants to explain it with the help of the classical mechanics. That is the wave nature of light. And according to the wave nature of light, what's happened? The emitted electron from the surface, energy of the emitted electron on the surface depends on the intensity of light. Okay, so he changed the intensity of the light, and he saw that when the intensity of light changes, electrons emitted simultaneously. Which means at there is no time delay. It is an instantaneous process. But if the intensity is low, then what happens? It takes some time because it takes some time. Why? Because the electron first absorbs the energy from the light, after then it is ejected. But he saw that when light is incident, the electrons are emitted instantaneously. Okay, so this is an instantaneous process. We cannot explain it also. Why the electrons are emitted instantaneously? Okay, because he considered that it is the common wave nature of light, and it depends, the energy of the electron depends upon the intensity of light. Okay, so he cannot, as I told you, he don't know the photons at that time, and he don't know the particle nature of the light, and he don't know the energy of the electron depends upon the energy of the photon, not on the intensity of the photon. Okay, so first Max Planck give the idea of the photon. Okay, in blackbody radiation. After then, in 1905, Einstein explained the photoelectric effect with the help of the quantum theory or the quantum mechanics. He considered the photon as a particle, and he first told that the energy of the emitted electron depends on the energy of the incident photon, not on the incident intensity of the light. Okay, so that is the photoelectric effect, that is the quantum mechanics. Also the blackbody radiation, we cannot explain the spectrum of the blackbody radiation with the help of the classical mechanics. Okay, with the help of the classical mechanics, because again we consider it as the wave nature of light according to the classical mechanics. Okay, electromagnetic wave. And third one is the atoms. According to the classical mechanics, what's happened? Rutherford theory. You know Rutherford? The electrons are revolving around the nucleus. And we know that when the particles is revolving, that means it has some acceleration. And according to the classical electromagnetic theory, what's happened? If the electrons are revolving or any charge is revolving, or an accelerating charge is emit energy. So the electron, when it is revolving around the nucleus, it is an acceleration, centripetal acceleration. So it emits the energy, and if it emits the energy, then what happens? It falls on the nucleus, that is the atom will crash. So it is not possible. So Bohr first told that with the help of the quantum mechanics, that when the atoms when the when the electrons are revolving round the nucleus, when the electrons are revolving round the nucleus, then when the electrons are in a certain orbit and when it is revolving, it will not emit any energy. Both told it. The energy of the electron remains the same. But when the electron jumps from one orbit to another orbit, then if it goes from here to here, it absorbs the energy, and if the electron comes here to here, then it releases the energy in the form of radiation. Okay, that is the quantum mechanics. So these are the quantum mechanics, and this is called the inadequacy of the classical mechanics. Inadequacy means why we go for the quantum mechanics. What are the experiment or what is the common phenomenon which cannot be explained by the classical mechanics. Okay, so this is the common reason why we go for the quantum physics or quantum mechanics. Okay, now we will start the black body radiation, which is in your syllabus. So before we start black body radiation, we start the radiation. What is radiation? What is radiation? Okay. When we heat a body, then what's happened? It emits radiation, electromagnetic radiation. That's all. When you heat a iron bar, then it becomes red. Why? Because it emits the red light. Okay, that is called the radiation. Radiation. Any heated body emits electromagnetic radiation. Any heated body emits electromagnetic radiation. Full stop. If the temperature of the body increases, the wavelength of the emitted radiation decreases. Wavelength of the emitted radiation decreases. Similarly, a heated body can also absorb. Energy incident on it. Can also absorb radiation incident on it. Okay. Now, emissive power. This is given by E lambda. Emissive power. The emissive power of a body at a certain temperature T, at a certain temperature capital T in Kelvin, okay? Capital T means Kelvin. At a certain temperature T, bracket For a certain wavelength lambda at a certain temperature T, for a certain wavelength lambda is defined as the energy radiated normally in vacuum from its surface per unit area per unit second and per unit second and per unit range of wavelength, per unit area, per unit second and per unit range of wavelength. Okay, so radiation emitted from the surface normally from a per unit area, per unit second, per unit range of wavelength. That is called the emissive power of the material. Okay. Now the absorptive power. It is denoted by A lambda. It is defined as the ratio of amount of heat Q dash, amount of heat Q dash, amount of heat capital Q dash amount of heat Q dash absorbed by the body to the total amount of heat Q incident on the body by the body to the total amount of heat Q incident on the body. Total amount of heat incident on the body, that is A lambda equals to Q dash by Q. Okay. So you can see that A lambda is always less than 1 because Q dash is the always less than Q. Q dash is the heat absorbed by the body and Q is the heat incident on the body. Okay, so this is the absorptive power. Now we go to the black body. Follow, what is the black body? Black body.
So body which radiate 100% of the incident.
It's a imaginary which absorbs all kind of light.
All the radiation incident on it, and when it hits the body, it emits all the radiations. Definition. A black body is a substance. A black body is a substance which can absorb radiations of all wavelengths. Absorb radiations of all wavelengths incident on it. And emits radiations of all wavelengths when it is heated. Okay? When it is heated. What is the example? The lamp black. Platinum black. Lamp black, platinum black are considered as almost perfect black bodies. Considered as almost perfect black bodies for practical use. Almost perfect black bodies for practical use. Okay? Because we know that it's an imaginary concept. Because there is no black body such that which can absorb all the radiations. It may be 99% or 95% like that. But if we put these are the pens. If we put these pens in the body, then it can absorb 99% of the radiation. So, how we get a use for practical use? So, this is the black body. Here there is a cleavage. Okay, and inside the body, inside this one, we put the paints. This paint, lamp black or the platinum black. Okay. Now, when a radiation, this is a very fine hole. So when the light or the radiation is incident to this fine hole here, then what happens? Maybe 99% of the radiation is absorbed here. Okay, 1% is reflected back. Okay, and here 99% of that 1% is absorbed. So in this way, all the radiation is absorbed inside the black body. It cannot get back from the black body. So this is the one practical black body. Okay. So this is the fine hole and this is the cleavage. black body for practical use. Distribution of energy. Fine hole.
বডি সাইজিং ম্যাটার করে
এটা ওই মানে কি বলবো তোমার ওয়েভলেন্থের যে সাইজ হয় খুব বেশি রেডিয়েশন ছিল না তাহলে কি হবে দেন রেডিয়েশন অলসো কামিং আউট ফ্রম দ্য ফুল না ওটা যদি বড় হয়ে যায়
ব্ল্যাক বডি যখন হিট করলে মানে রেডিয়েট করবে
না ঠিক না হলে রেডিয়েশন হবে
মানে এখানে যে ব্ল্যাক বডি সাবস্টেন্স which can absorb radiation
হ্যাঁ
অন্য রেডিয়েশন অ্যাবজর্ব করবে
হ্যাঁ এমনি ঠান্ডা অবস্থা অবজর্ভ করবে
হ্যাঁ তারপরে হিট করলে যে
হিট করলে তখন অলসো রেডিয়েট করবে
মানে এমনি রেডিয়েট করবে
না দেখুন কোন এই হলে প্রথমে তো রেডিয়েশন হলো হোয়াট ইজ রেডিয়েশন হিট না করলে কখনো রেডিয়েট করবে না ওকে এবার দেখো কি বল লিখলাম ডিস্ট্রিবিউশন অফ এনার্জি in the spectrum of black body. Means the radiate করবে but we cannot see it. প্রত্যেক object is radiating আমরাও radiate করছি but we cannot observe that value. We cannot measure it. When we heat, then we can measure that amount of heat or that radiation. We are also emitting the radiation. যেমন কি তোমার অনেকে থাকো এটা গরম হয়ে যায় রুমটা So now the distribution of energy in the spectrum of black body. When a black body is heated, in a uniform temperature, when a black body is heated in a uniform temperature, the radiation of all possible wavelengths, coming out through its fine hole, fine hole through its fine hole. The intensity of the emitted radiation is plotted as a function of plotted as a function of wavelength lambda at different temperature, wavelength lambda at different temperature of the black body. The intensity of the emitted radiation is plotted as a function of wavelength lambda at different temperature of the black body. So what's happened? As I told you, if we now heat the black body in uniform temperature, it must be in uniform temperature. Then what's happened? It emits the radiation through its fine hole. Now, okay. And now, if we put a probe in the fine hole, probe means which can measure the intensity as well as wavelength of the emitted radiation. Okay, which can, if the black body radiation. Now, if we put a probe means probe which can measure, that is called the probe. Okay, which can measure anything, that is called probe. So, if we put a probe here, which can measure the intensity and the wavelength of the emitted radiation. Now, the radiation is emitted from here. Okay, at a certain temperature. And if we plot it in a graph, then what happens? At different temperature. Different temperature means temperature of the black body. At different temperature of the black body, if we plot the graph, then what's happening? So if we plot it like this is the lambda wavelength and intensity, E lambda intensity of the radiation which is emitted. Okay, then what's happened? Then it emits all the radiation from 0 to infinity. Okay, if this is for the temperature T1, then another for T2. This is for T2 temperature. This is for T3. So this is the spectrum of the black body radiation. This is called spectrum of black body radiation. Spectrum of black body radiation. Spectrum of black body radiation. Where T1 greater than T2 greater than T3. T1 greater than T2 greater than T3. Now what is lambda m? Lambda m1, lambda m2, lambda m3. Lambda m, where lambda m is the wavelength at maximum intensity. Lambda m is the wavelength at maximum intensity. Wavelength at maximum intensity. It is not the maximum wavelength. It is the wavelength at maximum intensity. Okay? And you can see that as the temperature increases, lambda m decreases. Why? That is the Stephen's displacement law. Lambda m into t equals to constant. What is it? Lambda m into t equals to constant. Lambda inverted proportional temperature. Such that when you multiply lambda m1 t1 equals to lambda m2 t2 equals to lambda m3 t3. Okay, that is why as the temperature increases, the lambda m decreases. The characteristics of the black body radiation spectrum. Characteristics of black body radiation spectrum. Okay, so from this figure we can say the characteristics. What's the question? Number 1. At a given temperature, the intensity of radiation at a given temperature, the intensity of radiation increases with the increase of wavelength. At a given temperature, the intensity of the radiation, if you take T1, at a given temperature, the intensity of radiation increases as the wavelength increases. As the wavelength increases, attains a maximum value. Attains a maximum value. Attains a maximum value. Attains a maximum value and then decreases as the wavelength increases, and then decreases as the wavelength increases. Okay, so at first, as the wavelength increases, intensity also increases, attains the maximum value, and after then, when the wavelength increases, the intensity decreases. It cannot be explained by the classical mechanics. Decreases. Number 2. Number 2. The wavelength corresponding to the maximum intensity. The wavelength corresponding to the maximum intensity decreases. The wavelength corresponding to the maximum intensity decreases as the temperature of the black body increases. As the temperature of the black body increases. That is lambda n into T equals to constant. Equals to constant. Constant means lambda m1 T1 equals to lambda n2 T2 equals to lambda n3 T3, like that. Number 3. There is an increase in intensity. There is an increase in intensity with the increase in temperature. With the increase in temperature at all values of wavelength. At all values of wavelength. কি বলছে দেখো? Intensity increases as the temperature increases for all values of wavelength. If you take this wavelength, here temperature is low. As the temperature increases, intensity increases. So for every value of the wavelength, the intensity of the intensity increases or temperature increases. That means no cards cut each other. So the graph cannot cut each other. Number 4. At a particular temperature, the area under the curve, at a particular temperature, the area under the curve represents the total energy emitted. Total energy emitted. Which is found to be proportional to c to the power 4. Which is found to be proportional to t to the power 4. That is E proportional to t to the power 4. So what is the definition? That means the area under the curve. This is the area under this curve. Okay, so this area represents the total energy emitted by the black body at temperature T3. Okay, this area represents the total energy emitted by the black body at temperature T3. and it is found that it is proportional to T to the power 4. Which is the key law? This one? Stefan's law. E equals to sigma T to the power 4. Okay, this is the Stefan's law of radiation. This is the Stefan's law of radiation. Radiation. So today up to this one. Okay. In the next class we will explain the theory of this graph.